Okay, all right. Good evening, everyone. And so today is the first class. I think last week we had the introduction session of what is the industry is all about and what is ASIC flow, what is PD flow, and all that. Okay, and today morning we again had physical design make flow introduction. So that is more of giving overview to the whole people or the audience uh, who are kind of not knowing, or probably they might be wanting to learn and things like that. So that was the reason behind all these sessions. But now this is kind of we have starting the first session. Okay, and if you guys look at the whole course syllabus and all that, so it would be like kind of say something like this. Okay, so we have got digital basics, okay, and then CMOS basics. So these two sessions will go for next couple of weeks, because without these two knowledge, you won't be able to understand any of the other topics. Okay, and you might have read in the college or in your university, as a part of your a course or curriculum, but what you are going to learn here is at a different thing. Okay, now any gate that you are going to add in the design, why are you adding it, and all that level. So it's, you can say, like kind of you brushing up the fundamentals again. Okay, that is a goal for next couple of weeks, because I when I talk to people, they say call themselves a PD engineer, and they when I interview people, right, if I ask them, okay, a simple questions on CMOS basics, they are not able to answer. Okay, and it is even if you are very good at all the advanced nodes and all that, but if you are not able to answer a very basic concepts, then it's going to give you a very bad impression. Okay, so that is what I'm going to focus now. So irrespective of anything, the whole thing is that you need to know the basics part, so that you understand what is the meaning of PPA concept. Okay, yeah. Okay, all right. So, having said that, now the first topic that we would be touching is it's kind of say the digital design part, and it would be kind of refreshing for you guys, and um, I will share this recording with you guys as well. Okay. Okay. So when it comes to the basics, digital basics, right? What is that comes to your mind? So it is always we say like the numbering systems. Okay, that is the first thing that we get. Okay, and it would be like kind of you have a different numbering systems. So all the digital circuits would understand only the binary number system. Okay, and say some of you or almost all of you are from circuit background, I believe. Now, what is the numbering system that is used in your microprocessor assembly and all? Any idea?
Binary language.
Hexadecimal. Okay, and it would be like kind of something like this. All the op codes and everything, it would be all something like this. Okay, now, so why these are all important? Why these are all important? Why these are all important? These are all important because all the operations that happens, okay, based on this number system, say as simple as that, like kind of binary operations. So any CPU that you have or ALU operations that actually happens. Okay, Now they all happens with a, in the form of zeros and ones. Okay, and then octal and binary is what we use in our regular day-to-day life because currencies and everything. Okay, right now, so what are the basic things that you need to refresh? See, basically there are some people who are kind of new college grads, so they might go through written tests, okay, when they wanted to get into industry. So they might give you some decimal number and they ask you to write a binary, so decimal to binary conversion that you need to practice. So just get an formula or something like that, so that would actually help you. So decimal to binary and then binary to decimal. This is only for a new college grads, so who might be, say for example, when you try to apply to companies like end of say Nvidia or Intel or any other company. So there may be a written test. Say for example, Synopsys. There may be a written test in which they might give you one or two questions on these things. Okay, so you should know the conversion between two numbering systems. So it's kind of decimal to binary and then binary to decimal. Okay, and then you also should learn it's kind of binary addition. So what is the binary addition? Say for example, you have okay. Let me ask you this a simple thing. So 10 is one number. Now what would be the binary number for this?
1010.
Exactly. So it is kind of 1010. So how do we do this? So it's basically 1010. So this is going to be 2 to the power 0, and this is going to be 2 to the power 1. Say this is going to be 2 to the power 2, and say this is going to be 2 to the power 3. Okay. Now, having said that, okay. Now, okay, let me ask you this way. So what would be the number for, the binary number for 8?
1000.
100.
So it is going to be, say, kind of 1 000. Okay, so this is going to be 8. So now if you want to add these two, what is that you are going to follow? 1010, 1 000. Now what would be the outcome? What would be the outcome? No, let's go, but
100010.
let's go from, the way we do is from right to left, right? So 0 0, it is going to be 0, and 1 0 1, 0 0 0, and 1 1, it is going to be 0, and that is going to be carry of 1. Okay, now this is going to be kind of, now this is say 2 to the power 4, which is basically 16, and then this is 2 to the power 1. So now that is 2. So total 18. So this is how actually happens. So the whole system that we are actually going to learn, or the circuits that we are going to learn, okay, is going to happen in the form of a binary. Okay, so I would say arithmetic operation. So don't think that okay only addition. So there may be a addition, okay, and we may do subtraction, okay, and then there may be a multiplication and there may be a division. So all the kind of operations. So just get an idea, basic rough idea. So you don't need to get into too much of problem solving, taking 20 problems, 30 problems, not in that way. So it's simple. Say if I give you say 1010, so it kind of 10.2. Now how do you represent this in a binary? Okay, and then say for example, now say kind of 1000.01. Now how, what would be the decimal number for this? So just to get an idea. Okay, all right. So I don't want to spend too much of time on this number systems. I'm just giving you a kind of quick glance of what is that you should do, because the first few weeks, okay. Okay, so let me give a clarity on what we are going to do actually. Okay, so as I said, the first few weeks we would be covering this digital circuits and CMOS and then layout design. So you might wonder, so CMOS and all I've already covered in college or university and all, and layout also you had have covered it. Some of you might have covered it, and some of them, if they are from an electrical background, they might have not. Now, but remember, anything that you read from books, okay, in terms of layout, is completely outdated, okay, with respect to a digital circuits, okay. When it comes to digital chips or digital layout, so it may analog layouts and other things that are different, but when it comes to digital layouts, digital circuits layouts, for example, like standard cells or even memories, okay, they are all kind of outdated because the books are pretty old, and the technologies are kind of evolving, and every 2 year we keep getting one or two new technologies. So the way we draw the layouts and how you should look at them, all that are kind of changing these days. So that is the main reason why I'm actually covering so these two things. And then you have a Linux operating system. So I'm not sure how many of you are familiar with Linux OS, but all the execution happens in the Linux environment for us. All right. And then we will just walk through basics of the ASIC flow so that like you get an idea what are the different teams involved in this, and who is going to give you what inputs, and if you are missing some inputs to get started on the PD or synthesis, now whom you would approach, all that, okay. So ASIC or SOC design flow, and then you have a PDK and technology library. So when we say technology, say kind of you have a 7FF, and then you have a 5FF, or say 28 nanometer, or say 16 nanometer. So any technology that you talk or you wanted to pick up. Now what is that you need. Okay, so what are the inputs that you need to get it from foundries? Say, for example, there are what are the different foundries that that are existing these days? What are the different foundries that that they are existing these days?
Global Foundry,
Sorry, which one?
Global Foundry,
Global foundries. Okay,
TSMC,
okay,
Samsung,
okay,
XFAB.
Intel, Intel.
okay. All right. So these are pretty much the currently well-known foundries with the kind of latest technologies. So these guys are say 7 nanometer and up. They are all working on 7 and below. Okay, but I think global foundries have stopped even 7 nanometer. So they are targeting something higher than 7. Okay, so these are all the well-known foundries. Now, when you target these foundries, now you have to go and tell them, hey, I'm actually designing a chip targeting your particular foundry, this particular process. In 28 itself, you may have different process and all that. So you need to ask them for something. Hey, I need your PDK to get started my runs or my activities. Okay, and then technology library. So what are all the technology informations? What files, what formats, all that you need. Okay, so that's module 5. And then we will be talking about the standard cells and macro libraries. Okay, the standard cells and macro libraries, and these are all your inputs. What are the different views? So all that, and then timing constraints. So SDC, that's a basic thing that people would need if they wanted to get started with synthesis, and then PNR, and then STA. So all these things we will be covering. So I call this as a complete basics. Now, to be honest, actually, we would be having this. All of them are kind of more of a theory session theory, and I would say these guys say Linux you will have to practice, because I would be enabling you the lab credentials. You can actually practice. There will be sessions on Linux, and then I would be giving you assignments. I would be covering say PDK and what and all are there, and technology library what and all. So you would be given assignments, and you would be working. You have to walk through all those, opening the files and checking them, what informations are present in what, and then standard cells. Okay, what are the different standard cells? There are different heights, say kind of 6 track height or 10 track height, and then HVT, LVT, different standard cells, and what is the meaning of macro, everything that we will be covering, and then timing constraints. Say, for example, simple, if I give you a design, okay, so now how would you go and, develop a constraints for that, okay? So that is how it is actually kind of, we would be discussing, okay? Okay, for example, a simple thing. Now, if I give you a design like this, okay, now if I ask you to write SDC for this, timing constraints, okay, now how do you go about it? Okay, so that much level of depth that we would be covering. So it's basically, it is not just only understanding the SDC. In fact, if I give you a design, something like this, now how would you go and write the SDC part? So we would be covering to that extent. Okay, and then it is like kind of basic, learning the basic static timing analysis. What is the meaning of setup check, what is the meaning of hold check, and what are the different types of paths, into reg to reg, and the reg to out, and then into out, and all that. Okay, all these are, I call it like a basics. So this is the first thing that we would be covering. Okay, and then what we would be doing is we would be getting into the actual implementation part. So we would be getting started with this module 12. Okay, because these things we will be covering it little later. Okay, because our focus is mainly physical design, and once you learn the physical design, then you learning synthesis is more easier. Okay, so that you don't get bored. All right, so we will be getting started with module 12. Okay, the complete implementation part. Okay, with these are all, it's 100% practical. So it is like kind of, I would say, 95% theory practical. Okay, and 5% there is a concepts that you need to learn. Okay, and then you have got sign off checks. So once you complete your routing, then you have got a sign off check. So these sign off checks, we would be doing it completely, practicals, RTC extraction. So all these things would be kind of practical, except this IREM, because we don't have the tool. Okay, so we would be leaving this, and we will be covering only the theory part for this IREM. And let's say if you get a chance tomorrow, how would you go and analyze it? Just that you will not do the lab part, but I will show based on my experience, because I have used to the tool, and what options, what checks that I do, everything I will be covering with respect to this. But all the other things you will be covered in the, we'll have a labs. Okay, sign up checks. And then coming to the advanced topics, so these are all some things that really on the advanced side, say kind of low power and UPF, because what I wanted to do is a simple PD flow. So let's learn the PD flow first, simple physical design flow, and then we'll go and add say low power extra on top of it. Now, when your design is having a low power methodologies, now how you do that? So there will be few changes in the PD flow that you need to account. So that is going to be easy. So let's learn the plain vanilla physical design flow first. Okay, and then we will be adding. Say now one is low power, and second is, say for example, your lower nodes. Okay, lower nodes. Say for example, in case if you are using FinFET and double patterning, what are the challenges, and then everything. So 16 nanometer and 7 nanometer, all the floor plan challenges, DRCs and everything. So our goal is to learn plain vanilla physical design flow first, so that okay, what is a physical design engineer would be doing, and if given an opportunity, you would be able to go and execute the projects, right? And then adding these things on top of it. Okay, so that you have a solid base built. Now you go and add one by one whatever that you want, only the delta changes, incrementally changes, incremental changes that you have to walk through, or learn it. That is going to be more easier. All right, and then throughout your flow, the whole learning, you would be using make based flow is what we have as a environment here. All right. So that is how I'm going to carry out the whole session. Okay, and it would take uh, see for these two topics to complete, because these two are the main topics, it would take at least 3 to 4 weeks. I'm telling you the reason behind this, because whatever that you have read in your college, it is going to be almost one semester. Okay, which I am going to cover in say probably 2 hours plus 2 hours, say kind of in 4 hours. But that would be a more of revision, and then why are you doing this? But it would be a more of homework for you to revise the whole things. Now again, the same thing. It's kind of say 2 hours plus 2 hours. Again, this CMOS is going to be one semester paper that you might have learned, and we will not be looking at too much of circuit design and all. We will be looking at basic CMOS operations and the basic gates, how they operate. Now, how do you design a schematic, and how do you design a standard cell layout for that? And then you would be, how you use this and come up with the libraries, standard cell libraries. Okay, so and what are the different checks and all that. So first few weeks is going to be till we reach here. It is this basics all going to be theory massive. I'm just telling you upfront. It is more of a theory massive for the first few weeks. And once we cover this, once you are very solid in these fundamentals, the rest all are going to be cakewalk for you. Okay, so try to put more effort and try to brush up, and I don't want you to prepare in an exam mindset. Don't do that. There is no exam here. Understand that you wanted to design the chip, the next generation chip. Now you need the knowledge. You are not going to give any exam here, and just focus only on the knowledge. How you can learn the whole process, and let's say tomorrow how you can improve your say power, say your frequency targets, and then all that. So that should be the only motive. So no exam, please. Don't ever get into mindset of okay solving equations. Okay, don't do all that actually, which I hated. I myself does not like equations, so I don't want you to solving the equation, get into a solving mode of equations, deriving and all that. It's more of concepts that you need. Okay, for you to be a PD engineer, as simple as that. Okay, I would like to stop here for question and answers. You guys have anything that you want to talk?
My question is, can you share these slides with us?
I would be actually sharing it. I'm actually working on certain things, and I would definitely, whatever the slides that I'm actually using for my presentations for the class, I would be doing that. And plus, I would be actually, even sharing some of my OneNote class notes. See, you would have, you will see me using something like this. Okay, and I would actually write out a couple of things. This whole page I will convert it as a PDF, and then I would give you. So you will not be sort of any kind of documentations. So whatever that I'm referring, you will actually learn, you get everything.
Okay, thank you.
Because it is more of my running notes, so I might use this. See here, it's kind of for every batch I have something like this, so I might refer any of this suddenly quickly and all that. I would be actually, picking any of this and covering, and you will actually get this whole handwritten notes as a PDF. And whatever the slides that I'm actually referring, that also I would be enabling you as well.
Okay, thank you.
Okay, all right. So let's get back to our business on the. So I'm just winding up this number system. So just whoever is a recent passed outs, say probably 2023 and 2024 guys, or even anyone who's beyond that 2025, 2024, 2023. These guys will have to go through the written test part. So if you are coming with this any of this passed out years, uh, my suggestion is just look at from a written test angle. That's the only thing. Nobody would ask you to derive this and things like. There is no concept and all here much. Just that understand solve a couple of problems and then get a chance, get that, idea, and, and remember, I want you to put a notebook, okay, which you can actually have. So there are ways, this class is more of a practical side, and I will be writing like this and I will be explaining, okay, and you will get the recordings. But still, my suggestion is have one class notebook which you can actually write all the running notes and things like that. One class notebook, and then one, uh, say you can say your reference for the later part. So that is your reference notebook. This is going to be your detailed notebook that you would be writing after the class. Okay, so that is how this notebook is going to be. You can say, you can kind of a Bible. Okay, so it is like kind of, you can refer this. So class notes is, you might scribble it. Okay, you might not know the concept, but just write it. Okay, so if I say clock uncertainty, okay, you may not know what it is, but just write it, so that you can go and read it later and then put that whatever that understanding that you have got. So this is going to be a reference notebook, and I'm sure you will at least need minimum 3 to 4 big notebooks till, by the time we complete the course. And then one for your interview preparation, interview reference. So, which means all your assignment questions and important topics. So, you have to put it in an interview notebook, so that 1 hour before your interview, this should be your reference book. All the important points and everything. Okay, so this is going to be your rough book, just whatever that we talk, you just have to write it. And then this is going to be your, after you learning a concept, put it in your own notes, own writing, so that like when you wanted to refer it. See, there are many people who who attended my classes in the past. They actually keep these notebooks in their workplace. Some of them keep that, they just keep going through what kind of checks, because you don't need to buy it. So they just refer it. So something like this kind of, you can say, detailed explanations and everything. And then one which is short, only bullet points. Okay, so that is meant for in your interview purpose. So keep this these three things in mind, and there will be assignments every week. Okay, so by end of Tuesday, or Tuesday IST time night, you will have assignments be given, and before your next class you have to submit your assignments. That is going to be our regular practice. And your assignments first few weeks would be kind of more of a theory and referring to your environment and coming up with answers. But once we start with the lab, there will be more lab activities than your theory part. Okay, so this is something that if you are very serious about getting into a PD job, this is what I would request you to follow. All right, and you can ask anything in that group. Now we will be having a group that I will be creating, Telegram group, and you can actually, you will be added to the that group, and then you can actually ask any kind of questions that you have in that group. Okay, okay, all right. Getting back to the work again. So, what are the basic blocks in digital? What are the basic blocks in digital? So, we say two things. One is basically, see, when we say digital, right? See, there are certain inputs. See, this is, you can say, this is a system. Okay. Say this is a system. Now, you are giving some signal inputs and you are actually getting some outputs. Now, what is this system is going to do? It is going to perform certain operations that you have actually been designed. Okay, now what this is how your digital systems would be. All right, now here if you look at here, combinational blocks, so there are different types of systems, right? You can look at only a combination. So combinational logic meaning what? So you give your input, okay, and then there is there are certain gates that would actually take these inputs and process them as per their Boolean logic, or the whatever that is the functionality, and then the output would be computed. Okay, now the basic thing here is when you say combinational, your inputs does not depend on anything else. It just they just only on the present input. There is nothing else that it would depends. The moment input changes, your output will change after sometime. That is something that we call propagation delay. So we will talk more on that delay and everything. Okay. So this is basically a combinational logic. So what does that meaning? Logic blocks whose output logic value depends only on the input logics, inputs. Okay. Now there is a second type. Okay. There is a type two which you can call it like kind of the sequential logic, which is basically it depends on your present input and then your information that is stored. Okay. It past output and things like that. So that means your when you say sequential logic, they are kind of input, current input plus and the state, current state of this registers. Okay. And now when you say this, the system can be represented by with the help of say truth table or Boolean functions or say Karnaugh map. Okay. So you can actually so predominantly it would be kind of they will express it in the form of Boolean functions. Okay, that's what more of you might have seen in textbooks or truth table and etc. Okay, but these days the industry is actually would be giving you okay, I wanted to build say PCIe 5, okay, or say DDR say kind of 4 or 5 or whatever it is. Okay, otherwise say Wi-Fi 5 or say 6. So these are all the kind of spec. Now when you work on the design side, you will go through all of this spec in detail and then you will implement. But when it comes to smaller circuits and all that, so they'll be just using the Boolean function to express it. All right. Okay, so I wanted to walk you through a quickly the basic gates. Okay, what are the different basic gates that you see in this picture? What are the different gates that you're actually checking or you're seeing in this? Okay, so the first gate is basically a inverter. What is this inverter? Inverter or not gate? So we actually represent this inverter using this kind of picture. Okay, it is kind of you can see anything that you give input that is going to be a inverter. Say it is like B is your output, and when you write the equation, it is always expressed with respect to input. Now it is kind of A dash or A bar. Okay, so this is going to be a truth table, and based on the truth table, when you write the equation, it is going to be kind of B equal to A bar. That's your inverter. Now buffer. Okay, now buffer meaning two inverters that are connected back to back. Okay, that is the meaning. So don't take it in any other way. So it is kind of we always look at kind of two inverter connected back to back. It's kind of connected one after other. Now what does meaning is when you give zero, it's just that the output is going to be zero, and then when you give one, the output is going to be one. But why do you need buffer? Why do we need buffer? See, buffer is used to improve your signal quality. Now, if you look at, say, for example, you may have a designs where you may have, say, something like this, under gate, okay, driving a long distance. Okay, say kind of 200 micron distance. It's a long net. Okay, now so this is a assume this is the actual circuit. Okay, now what will happen is your output would be kind of, when it is coming out, it would be say kind of like this. It is going to be kind of a strong signal, but when it is passing through this net for a longer distance, so there will be a R and C. Okay, R, and then there will be a gap. Now when it is passing through all this, the transition at this input pin would get degraded. Okay, the transition at this input pin would be degraded. Now this is going to be a problem. Okay, this is going to be a problem. Now what we do is, you need to restore this transition. Okay, you need to restore this transition. Now for that purpose only, we would be having the we need to add the buffer. Now when you add a buffer here, where do we add a buffer? So we might add it in the middle. Okay, now what will happen is, it actually picks that same signal, whatever that is coming over here. Now and then the output of this, the quality of this is kind of say improved. Now so this overall, the transition is kind of improved. Now we need buffer. Okay, to maintain your transition. Okay, that is as simple as that. So why do you need a buffer? So that's a question that you might come across. Why do you need a buffer? Where do you use this buffer? So this is the answer that you should be giving. Got it? Any question here? Because there's something that on the practical side that we do on day-to-day basis. So any question here? Okay. So the next gate is your AND gate. Okay. Now AND gate functionality is like when both the inputs are one, the output is one. Else it is going to be zero in other conditions. Okay. Now this is the truth table, and this is what you wanted to write as a equation. So it is basically your output C is equal to A dot B. Okay. And then the next one is basically OR gate. Now, OR gate is basically when any one of the input is 1, okay, your output is going to be 1. Okay, in other case it is going to be 0. So when both of them are 0 0, then it is going to be 0. So as I said, any one of them is 1, then your output is going to be 1. So now if you look at here, it is a plus symbol, that is basically OR. So C is equal to A plus B. Alright, and then you have got a NAND gate. Okay, you have got NAND gate. Now what is this NAND gate? It's basically AND then plus an inverter. Okay, okay, so let me give you a simple assignment question for you guys. Which is bigger in terms of area? Okay, which is bigger in terms of area? Bigger in terms of area. So it is the NAND or AND. Out of these two, which is bigger? That is a question that I have for you guys. That's your assignment question. Now, I don't want to discuss the answer now. You can actually spend some time, because if you know this, you would understand, okay, what kind of cells that you wanted to use, and what is the advantage of you using, certain cells and etc. Okay, just go through this, topics now, basically the area and the logic, and which is kind of, higher and everything. So I would be giving you this answer probably after a couple of weeks, because by the time you will get to learn that. Okay, so NAND gate is basically AND then one inverter. That is your NAND here. Okay, so that means this output is completely inverted. So it's basically when both of them are 1 1, the output is 0, else it is going to be 1. So now what does this meaning is? So it's basically A dot B, the whole bar. All right. and then NOR gate. So it's again the same thing, OR then plus one inverter. That is actually a NOR gate. And when you have, when you have an OR gate, right, and then you just add an inverter. Now you see here, there's a truth table, and adding inverter to that is going to be 1 0 0 0. That means when both of them are 0 0, the output is 1. In other conditions, it is going to be 0. That is what it is. So it's kind of A plus B whole bar. So these are all again the basic gates, okay, and they are, we are not done yet. There are two more gates that you are actually going to look at. So one is basically XOR gate, okay. When you have XOR gate, right, like where do we use this XOR gate? Any idea? Where do we use this XOR gates?
Switches.
I did not get that. Which one? Okay, simple thing. Now, do you know there is something called a comparator? Okay, so how do you access your emails? How do you access your email? So you enter your username and then you enter your password. So the password is being checked. When you created a account, email account, that time you would have been you would have used a certain password. Now every time you wanted to access, we would be checking this password. Is it same as what you have given at the time of creation? Now, what is that? It's basically a comparator. So it compares your the password that you have given and then the password that you are entering now. So that to avoid unwanted access. Right now, the hardware model of this. Okay, you see a simple comparison here also. Okay, it is going to be just a simple comparison, string comparison or whatever it is. Okay, but in the hardware model, it is going to be implemented either in the form of XOR or XNOR. Okay, XOR or XNOR. Okay, so the equation is basically A B bar plus A bar B. That is a form equation. Okay, and then when it comes to XNOR, it is again a simple adding an inverter to that XOR. Now this is going to be a Boolean equation, and then if you write it in expanding manner, it is going to be A bar B bar plus A B. That is your X NOR. Okay, so these are all your basic logic gates that we would be having in our designs. And remember, when I say basic logic gates, so the functionality of these gates are the similar. No, that's all. But if you go and check in our library, standard cell libraries, okay, the standard cell libraries, okay, you would actually have many more gates. Okay, I'll just show you guys what are all the different things. Okay, 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 I can see. So I you will learn all these tricks whatever I'm using now. You will learn all these tricks when we get into Linux. Okay, so if you look at, right, this particular 28 nanometer, whatever that we have, is having a 350 different cells. So what is that you have seen just now? So you have just seen only kind of say six gates. Okay, that's a basic gates. All right, but when we wanted to design or when we wanted to implement something, that is going to be, so coming from your something called standard cell library. So this would be given to you by someone else. Okay, so you will get a chance to learn all that. I'm just telling you that there are 350 different cells. So you have AND gate, OR gate, and etc. Here we have a 350 cells that are there. Okay, now you see here it is kind of see AND gate, four input AND gate. Now what you have seen was only two input. Okay, but you see here there are four input AND gate, and then again four input AND gate. All right, now what is this? Okay, so there is a homework that I wanted to give you. So you see here AND 4, that is a 4 input AND gate. And what is this X1, X2? This is something that X4. Now these are all some things that we call it. AND 4 is one part, that is your function. Now this X1, X2, these are all a different thing. And then there is something called HVT, HVT, HVT. What is this? So if you ask me, it is a function is the first thing. Okay, then the next is drive strength. Drive strength, so just write it, what is drive strength? That's your homework. Okay, and then there is something called VT library. So it is multi VT. Okay, now when I say function, you may have an AND gate. Okay, NAND. Okay, and then you have OR, NOR. So there are many such things. Now, what is this drive strength? So you may have something called X0, X1, X2, X4, X8, X16, and things like that. So these are all something called drive strengths. And then multi-VT. So you have a HVT, SVT, and then LVT and ULVT. So these are all the different VT flavors that you would see in the library. So the homework for you is, what is meaning of drive strength, cell drive strength in VLSI? Okay. Okay. And how does it, why do we need these many drive strengths? Why do we need these many drive strengths? Okay. That's the first thing. The next thing is you have something called multi VT. Okay. It's basically a threshold voltage. You will get a chance to learn, but you can just go and, learn something about multi VT libraries in the VLSI. Multi VT libraries. And you can actually note it down, what is this HVT, SVT, LVT, ULVT, and all this. Okay, all right. So I've just showed you how many different cells that you would see here. Okay, so as I said, one such thing is say AND gate 4 input, AND gate 3 input, and AND gate 2 input. Okay, now with this AND gate itself, so how many different cells that you are seeing? It's kind of 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 cells with only AND functionality. Okay, so these three are your 2 input AND, these three are 4 and 3 input AND, these are 4 input and then you have now say something like AND OR. See here it is, what it is? AO cell. What is the meaning of AO? See, you will see something like this kind of cells in designs in the when you get into industry. AO, AOI, OA, OAI, then IOA, all this. Okay. So what is the meaning of this particular thing? What kind of function are they? So this is AND OR. AND OR. This is AND or invert. Okay, and this is or and then this is or and invert. Now this is invert or and. Okay, so these are all the different types of families that you would see. Okay, you can check here what are the different cells that you see in the system. Okay, see here you have got AO. Okay, and then this AO, and then see here it is kind of AO to different inputs, the number of inputs. So it is and or, but it's like if you look at here triple, what is this meaning is, see, see there is a and. Okay, now there is another and. Now this is a R. Okay, now this is going to be say kind of A, B, C, D, and say this is Z. That is the meaning of AO triple two. AO triple two. AO double two. So there are different number of inputs and all that. So you might now if you want to learn more about such things, when we get started on the lab part, I will explain you where to look for the detail. Understand that this is a kind of and or structure. That's a basic thing. Okay. So any question on this basic gates and then beyond the basic gates, what is the meaning of drive strength and then different number of inputs and then what is the type of VTs? Any question here? Okay. Now,
Hi, Kumar.
hi.
Yeah,
Go ahead.
just a question here. You just showed us actually AOI, IOA, and like
Correct.
combination of inverter and OR.
Correct.
So only why these combinations? Why like other combinations are not there? Why?
What is the meaning of
So where
other
exactly we
combination?
use this combination?
No, no, wait. So
So there are
when
many standard cells, right?
correct, correct. We have other combinations. So inverters and then inverted buffers and then so you have I'm just showing you. You can see. Hope you can see the things.
Okay,
Right? Yeah. Okay.
okay, okay,
See here NAND 3x0 HBT and MUX. See, it's simple, right? Like what is that will help you saving your area. That is the basic thing. Okay.
okay.
Now, see a simple question. Let me ask you a simple question. Now, see this is AND gate, and then you adding an inverter. What is that? It is going to make you. What is the functionality?
And this NAND gate.
Okay. Now there is a NAND gate. Now, among these two, which one would you prefer when you are implementing a design?
I prefer NAND gate
Why?
because we need to place two cells rather than placing two cells. That will save area, and we can actually combination and we can do in a single cell.
Okay. So you made the point area.
Yeah.
Okay. Now say the same thing. Say assuming this is AOI. Okay, and then now you go and build individual AND gate.
Mm-hmm. Got it. It will
So
take more area.
now, so if why, first of all, why we have these many cells in the library? That's the first thing that you guys have to ask yourself. Okay, now what is our goal when we are building a chip? Our goal is to achieve our PPA targets. Okay, because silicon area is not less cost, it is a costlier, one of the costliest thing. Okay, now having said that, you should always target which is going to save your power and save your performance, or get you better performance and less area. Now, if you have a cells which are kind of with the different families, with the different functionalities, now instead of doing all these, okay, individual cells, the tool might pick the cell which is kind of AOI related, AOI family. Now that will have a less area. Okay, this will have a less area. That is the main reason why we go for a lot of different families. Okay,
Okay.
that's a basic thing.
Can I ask a
Okay.
question, please?
Go
So
ahead, go ahead, go ahead. See, this is a kind of more of an interactive session. You can stop me and ask questions. I would be happy to answer.
Okay. In the first one, AND gate and inverter in the top of the design.
Okay, so let me just to understand that okay, say this is one,
Yeah.
say
Yes.
this
Yes. I
is two.
understand.
Okay, now
Sure.
say I'm just marking
Uh,
it, say three, four, so that when you talk about it, I can refer what number. Okay, yeah, go ahead.
sure. Uh, when you are discussing about the area, but 1 and 2 is the same, right? How is it the different
In
area?
terms of function, they are same. Okay, but in terms of area, this is going to be more area, but this is going to be less area.
Okay.
Okay, so if you want to understand this, okay, okay, you continue. Then I'll open the things and I will show you what is the area. Okay.
Okay. I understand. I understand what you mean. I understand.
Okay, so maybe the other guys are new, they may be new college grads and extra. So let me just show you guys what is going to be the area of an AND gate and then an inverter and then an AND gate. So let's pick for our understanding. I'm going to pick, say, AND 2 x0 underscore HVT and then say inverter x0 HVT and then this is one combinations and then NAND 2x0 underscore HVT. Okay, I will just pick up the dot lib and then I will just show you guys so that you understand it. Okay, okay, so the area of this particular cell is basically 1.524. Let's just keep it like kind of for our reference, it is 1.524. Okay, now say the inverter. Okay, now this is 1.27. That is your area, 0. Okay, now I wanted to now look at the NAND 2 x0 underscore HCT. Okay, now what is this actually? This is basically now 1.524. Okay, now this whole combination, if you count it, now it is going to be approximately 2.794. Okay, now the same thing when you build that using one cell, the area that you have is this. Okay, now that is the reason when you can put more logic and create it as a one cell. Okay, this NAND is we call it like a one gate or one cell. Now the same way AND or invert, this also we call it like kind of one cell or say one gate. Okay, now you can easily understand that. Okay, here.
Okay. I got it. Thank you. I got
Okay,
it.
so now how this area is saved, all that I would be able to explain when we get into layout portion, layout topic. So that's why I said CMOS basics designs, basics meaning I would say schematic. Okay, and then you have your layout part. Okay, so your area, this area is comes from your layout. So when you understand your layout basics, you will be able to explain this in a better way. Got it?
Okay, I got it. Thank you.
Hi, sir. Sorry for
Hi.
interruption.
No worries. Go ahead.
Uh, you are explaining an area like 1.5 to 4 to point. This area, in terms of which SI units, it's nanometer or something
It is a
other.
micron. It is kind of mm squared something. It is a kind of whatever that is defined in this file. If you look at here, see there would be units that are defined. See, you see here. So for each of the things, so when it comes to timing, 1 nanoseconds. When it comes to power, leakage power, it is a 1 picowatt. And when we say anything about voltage, it is 1 volt. Okay, and when it says anything about current, it is 1 microamps. And when we say anything about cap, it is all femtofarad. So area is going to be kind of micron.
Yeah. Okay, sir.
Okay, yeah. Okay, all right. So the next thing that I wanted to talk here is, see, universal gates. What is this universal gates? What is the meaning of universal gates?
So that one gate can operate more than
I cannot hear you properly. Anyone else wants to add?
With the help of universal gate, we can make more logics, whatever we need.
Okay. So the thing is that, so using these universal gates, you can realize any logic. That's the exact word that I wanted to use. Okay. Using these universal gates, you can realize any logic. As simple as that. So you may need, say it's kind of, you can use it like something like kind of, spare cell. So spare gate or spare cells in VLSI. So this is another homework. What is the spare cells? Why do we need spare cells? Okay, try to spend some time on it. So on that spare gate and spare cells, why do you need spare cells and when do we use them and all that. So these universal gates are pretty much used to implement any logic. Okay, to implement any logic. When I say any logic, it can be any Boolean logic that you can build. Say you may have a kind of using NAND. So you have a NAND gate. Now a simple thing, now how do you build your inverter out of NAND gate or using NAND gate? Using NAND gate, inverter using NAND gate, or buffer using NAND gate. Okay, so it would be more of NAND configuration. NAND configuration. That is a basic thing. Okay. Now the same way you can use NOR gate also to implement any kind of logics, and then so in textbooks you might have seen only NAND and NOR, but when it comes to our industry, you have multiplex, MUX as one of the standard cell. Now if I have to show you here, okay, so there are MUX. Okay, you see here, there are 2 cross 1 MUX and there are 4 cross 1 MUX. This is one, cell. Okay, it is also given as a one cell. That is why I captured this as a, universal gate. So basically in textbooks you will see only NAND and NOR. Okay, but when it comes to industry, we also use MUX as a spare gate, or you can say call MUX as a universal gate as well. All right. So you using these three, any of these three, you can realize any kind of logic. Okay. Let's go over it, briefly. Okay. So okay. Now simple, right? Using NAND gate. Now how do you build an inverter? Okay, how do you build an inverter? So now, if you look at what is a logic, the truth table, 0 1 1 0 1 1, NAND gate truth table, what it is? It is going to be this. Okay, yes or no? Now, how do you build an inverter by looking at this particular, truth table? See, you need to understand that, when you connect this to 1, what is actually happening to your other input? When you give 0 to the other input, it is basically output is 1, and when you give 1 as an input, that output is 0. Now, what is actually happening in this scenario? Isn't it this inverter? Isn't it this inverter? So this is one scenario, one way of you implementing. Now there is a look at another way, that when you have both the inputs tied, both the inputs are same, the output is going to be opposite. This is another way. Now what is this meaning is, you have a NAND gate, okay, one, so both of them are shorted here. Both the inputs are shorted. So this is case one, and then the another one is you connecting it to VDD, and this is kind of say B. Now this is going to be say Z. Now this is case 2. Now both of them are actually the same thing. Now if you look at what, you have a NAND gate, okay, and your output that you wanted is basically an inverter. But the way you implement, okay, now one is you shorting both the inputs, and the second is only one input is, one of the input is connected to VDD. All right. Now the homework for you is, you are actually building an inverter using NAND. But now among these two, which one would you prefer? Which one would you prefer from a STA point of view, from a static timing analysis point of view? So this question that you have to answer probably middle of a course, when you are halfway through the course, or when we cover the STA basics. Okay. So which one would you prefer, ideally speaking? That's your homework. Okay. Now moving on to the next one. So this is something that AND gate. It's like kind of using the NAND. We are actually trying to realize the AND gate, and the same thing OR gate. Using the NAND gates, only NAND gates, we are actually realizing the OR gates. Okay. Okay. So this is the, you can just probably note it down. So try to implement this particular logic using only NAND configurations. Anyway, you will get the recording. Basically, you can actually go through that.
Can I ask a question, please?
Yeah, go ahead.
What is the benefit of using NAND? Why we are using NAND? This kind of.
Okay.
What is the benefit of the using NAND gates? Uh, we can use these gates also. Why we are using NAND gates? What's the benefit?
Okay. Can I answer this question after 2 weeks? And can I answer this question after 2 weeks? Because you will automatically get your answer.
Okay.
The reason behind this, I need to cover basics of CMOS, and then when we get into a CMOS circuits, you would actually get an answer why we prefer NAND compared to any other gates.
Okay.
But what I am trying to cover here is from a universal gates point of view, so that like um, there is something called spare cells in the VLSI. So PD guys will have to add spare cells, and then that would be always universal gates, because you don't know whether the chip will work 100% sure or not. If there are any bugs that found, you would actually use these parcels to repair that or fix that bug. So it's a kind of when you are having a car, when you are going in a car, you would ensure always that stepney is there. Okay. So this kind of sprinkled everywhere in the design. Say for example, if this is your chip, okay, this is your whole chip. Now you will have different blocks, Okay, so you have a different blocks. Okay, now we actually go and add this kind of universal gates, everywhere, just for any future, work. Okay, it is a kind of everywhere we add it. Okay, now what is the advantage of it? So there is a topic, pre-placing the standard cells. That time I will be covering the spare cell logic, what is a spare cell and all that. Okay, so you can actually, you will get to know. But in case if you guys want it, okay, this was my blog which I used to write probably a decade ago. Okay, so I have given you guys what is the meaning of spare cells, and why do we need. So you will, I will cover in detail. Probably you can actually go through this. So there is a blog spot. It's called EDA automation. Okay, you will have something called spare cells. All right, so you can actually go through that to understand what is spare cell and why do you need it, and where do we use and all that.
Just a quick question. So,
Yeah.
what is the percentage, or like, is there any number like you use like these many cells
I
or these many percentage?
see it is like kind of we always go for maximum 5.5%, or every 100 by 100
Okay.
we would sprinkle couple of cells, as simple as that. Maybe 5 cells or 10 cells, something like that. 100, every 100 micron by
Okay.
100 micron we would try to sprinkle couple of NAND and a couple of NOR, and etc. So
Okay.
point
Okay.
0.5 to 1% is what the maximum you will have it in the designs. Okay.
Okay. Yeah. Thank you.
Okay, so moving on. Okay, so we were actually talking about this universal gate. So try to learn how do you implement the circuits using NAND and NOR. Okay, just walk, go through certain basics, and we will uh, implement, or you will actually learn this in the physical design, that or you will have to implement a certain logics. Okay, I would give you an assignment where there is a logic change that is actually need to be executed or need to be done before tape out. Now you have to redo it manually. Nobody is going to help you. So that they'll just tell you, okay, this is a particular logic I'm looking at. Now you have to, make changes incrementally. Now how you have to use this parser. So you would get to know all this. So there is, okay. The term that we use for all this is, say, something called functional ECO. Okay, just write it down. What is the meaning of functional ECO? Okay, that is the term that we use. So universal gates used, they are used as a spare cells, and now we implement functional ECOs using those spare cells when we are very close to tape out. Okay, moving on. Boolean algebra. So it's basically, all these theory parts I just wanted to skip. So truth table. So truth table is something that you guys know it already. We are just talking about AND gate truth table, OR gate truth table, and all that. So it's basically, a method to express the inputs and output, relations. Okay. And you will have, say, for example, if you have n input variables, and you will have a 2 to the power n term, entries. Okay, so it's a kind of two inputs. Then there are chances that 2 to the power 2, so you'll have a four entries. So it's basically 0 0 0 1 1 0 1 1. All right, and then, okay, so the way I go about it, there are many people follow different aspects of circuitry design. Okay, but if you ask me, I always write the truth table first. Okay, write truth table. Okay, then try to solve this based out of looking at the truth table, then come up with the equation. Okay, Boolean equation, which is kind of say optimized. To get this, okay, from this truth table and here to here, you might use Boolean theorems. Okay, you might manually, try to optimize. Okay, Boolean theorems or K-map. Okay, any of this you can actually use. All right, and once you get the optimized circuit, optimized equation, you can actually, go through, go and draw the circuit. Now, this is the process that I always follow and I want you to follow. So some people, by looking at this, they don't follow either Boolean theorems or K-map, and then, you know, they would try to, come up with the things. See, mainly when you come up with a process and then you follow the process, your output would be kind of, consistent. See, why I'm telling you this is, see, when you are going for written tests in companies, you tend to, be smart, but you might be making a silly mistakes and you might come up, choose a wrong answer. But if you follow the process, whatever it is, so there might be a 2 minutes time for each questions. I understand that, there may be time limits and etc. But you have to understand that there is a process that is there in place which you wanted to follow, and then get an optimized equation and then draw the circuit, the gate level circuit. Okay, this is supposed to be a process. Okay, now a simple thing here. Now tell me one thing on a simple note. I am concerned about my power performance area. Okay, now assume your delay of a cell is 1 ns and your net delay, okay, zero point 0.5 ns. Okay, now what would be the overall time? So I have a three circuits which are all same thing. Okay, now which one would you choose in terms of delay? Which one will have a lesser delay? And next is, which one will have a lesser area? Which one will have a lesser power? Can you guys tell me what would be the value here? Just letting you know that, this is one net, this is net one, this is net two. So something like that you have to consider, so you don't try to, consider too many things. Say one, two, three, and then you have again, say, kind of, this is one and then there's two and then again one, two. Now if you look at here, one, two, so this is going to be three. So each of this you have to learn through and trace through, and then tell me how many, what would be your overall time when there is an input change, how much time it will take for you to reflect at the output. Can you guys quickly solve it?
The first one is 12 nanoseconds.
First one is, so it is like, what you are saying is it is going to be this much, 12 nanoseconds. Okay. Okay, and what about second? What about others? I see many people in the call. Are you guys trying to calculate?
30 nanoseconds. The second one.
Okay. 13. Okay. Anyone else?
The last one, 8 nanoseconds.
Okay.
I got 7.5.
Okay, fine. What about others? What about others? What about others? We have many people. Just try to make it interactive. So when we are giving a problem, just try to solve it. You see, there's no one is going to judge you. No one is going to judge you. Okay, everyone are here to learn. Okay, now let's do this. Okay, whatever the answers that you guys, two guys have given me the answer, but other guys have not given me the answer. Okay, so I want you guys to start looking at giving answer from the next class. Now a simple thing. Now A to Z. So the first answer that I got was 12 ns. This one was 13 ns, and this one was kind of say 7.5 ns. Okay. Now a simple thing. So there is a net one. Okay. There is a cell one. So that kind of zero point 0.5 ns, and this is 1 ns. Now this is going to be zero point 0.5 ns, and say this is going to be 1 ns. Okay, now what is the total? When there is a change in A, how much time it will take to reflect at the output? 1.5 to
Three.
2.5,
Three.
and then zero point 0.5, so it's going to be 3 ns. So that is the answer. 12 is not the right answer. So I don't really understand why you guys are counting everything. That is not the way. So it is kind of the way, the path, okay, which is the longest path here. Now if you look at here, one. So now there is a one more path which is kind of on the longer side. Now if you look at here, say there is a one. This is going to be the longest path, ideally, if you ask me. So let's do this. Zero point 0.5. So there is a one, and then zero point 0.5, and then one, then zero point 0.5. Okay, and then one, and then zero point 0.5. Now if you look at here, say zero point 0.5 plus 1, 1.5, 2, 3, 3.5, 4.5, and actually this is going to be 5 ns. So the delay, you need to identify, there is something called logic levels. Okay, logic level. So that is what will give you the more delay. So you need to identify the critical path or the more number of logic levels, whichever is having a more logic levels, and then calculate it based on that. Okay, so here the logic level is kind of 1, 2, 3, cells, and then you have got a 4 nets. That's a maximum thing. Now here, so this is actually a 5 nanosecond is the right answer, maximum. Okay,
But if three inputs are changing, then
it doesn't matter, any input is changing, there will be output which would change within 5 nanoseconds maximum.
so because A has to travel through NAND and B has to travel through another inverter and NAND, and then C has to travel through inverter, NAND,
No,
and then OR, right?
no. If you look at here, there is a which has to travel through this inverter, and then it is all.
So
Okay.
we will consider the longest path, right?
Yeah, exactly. That's what I said, critical path. That is the longest path.
Okay.
So you need to identify which is the See, the way I look at, right, this is how you have to look at your timing aspects. Okay.
So if like input actually, say for instance, ABC actually, if all are three are zero, and then actually if all three are changing to one, so then also we have to take only the worst case path, only one signal net path, right?
Sorry, come again.
Say actually instance actually for like input A, B, C, all three are 0, 0, 0. Okay. So and then all three actually are changing to one, zero to high.
It doesn't
So at
matter.
that
No,
like
no, no.
situation.
Wait. You cannot go with that kind of assumption. What matters is how
Uh-huh.
much time. See, your combinations can be anything. Okay. Now,
Okay.
how much time, maximum time for it, the whole circuit takes to give, to change at the output or give you new output.
Mhm.
All right.
Yeah.
So basically, you need to identify the longest path, and then you need to calculate the timing. What is the overall delay perspective? Okay. Now,
Okay.
if you look at here, there is a one, two, three. But now, if you look at here, one, two, three, four. Got it? So this is going to be the longest path. So now you need to calculate the whole things based on this. Got it? So it is the same Boolean equation, the same functionality, but you are actually kind of implementing it using different way of different circuits. Okay, without optimized and optimization and etc. Now, ideally speaking, if you look at here, this is going to be the best thing in terms of everything. So power, definitely yes, because one, two, three, four gates will consume less power, and area, again four gates will have a less area, then more number of gates, and performance wise. So if you look at here, there is a one, two, three logic levels, one, two, three logic levels. So this both of them, this and this are equal, but power and area, this is best. So we have to choose from a PPA angle this circuit. So this is why we say optimization is really, really important. Okay. See, this is just a first class. So many of you are kind of might have lost touch with the digital fundamentals, but moving forward, when in the upcoming classes, you will slowly get a chance to, improve everything. Okay. Okay. All right. I think I wanted to stop here, guys. We'll continue next class. Okay. I'll share this recording with all of you, and it will be uploaded in the YouTube. Okay, and I will send out the link as well. All right. See you in the next class. You will hear from me on the next class through email and WhatsApp. Okay. Bye, everyone.
Hi. Bye.
Yeah, go ahead. I'm here. I'm here.